All right, non-calculator number 2 here. Uh, question 1. A bug travels or begins to crawl in a vertical up a vertical wire. So you got a wire like this. He's starting here at time equals 0, and this represents his motion. The velocity of the bug at the time is given by the graph. So this graph is velocity, so v of t. Now, at what value of t does the bug change direction? Absolutely right. The answer to this one is 6 because it changes from positive to negative at 6. So velocity changes from positive to negative. Which means that if the bug is going one way and then he changes direction and goes the other way. So if you're looking for any type of velocity or directional change, you're going to want to look at velocity. Yes?
So why couldn't it be number 4, because it's decreasing. Like, why isn't it not 4?
Well, think of the relationship between velocity, position, and acceleration. Now, when we do velocity and we do a sign test on velocity, we look for the zeros, right? So in this case, we look for the 0 at 6. Now, what type of values are here, positive or negative? Positive. So even though it's constant right here, it's still a positive velocity, which means your bug is moving in a positive direction, which would be up. At t equals 6, that's when he starts going here. At 2, he's here. And then, like, t equals 2 here. And then he just hangs out there for 2 seconds. So I guess he got tired. And then he decided to slow down a little bit, and then he said, why am I doing this? So he decided to go into a negative direction. So we don't know about the motivations of the bug. However, we do know that, and this is a key thing, when you're talking about velocity, and when you're doing this type of problem, and you're looking at this, and you're talking about velocity, think of velocity as a derivative of position. And then you can look for critical values. And you can find out increasing, decreasing based off of that idea, which is what you want to do. And that's part of this whole idea of what we're doing with why I'm giving you these specific types of problems. Because when you're dealing with the velocity, you're usually dealing with a derivative of the position. And a positive velocity means we're going in a positive direction. So when v is positive, we're going in a positive direction. When v is negative, we're going in a negative direction. Or even at 0, like Sean said, that's when we change direction. So wherever velocity is 0, so v equals 0, and it goes from positive to negative or negative to positive, that's a change in direction. Does that make sense? Good. So we got that. And then it says, what's the total distance the bug traveled? Well, obviously the answer is 13. But how do we get that? We do an integral. But what's the easiest way to do that with this? Say that again? Make triangles, count boxes, find areas. So if you just do this, That's 2 by 3. That's a triangle that's 2 by 3. So that area is going to be 3 because it'd be 1/2 times 2 times 3. So that would be a 3. Now what's the area of this part right here? 6. Now what's the area of this part right here? 3. Okay, good. Now what's the area of this part right here? It's 2 by 1. It's 2 by 1, so it's 1/2 times 2 times 1, which is 1. Now, the big question is, are we looking for where it ended up, or are we looking for total distance? Total distance. So if we're thinking about total distance, always think about, all right, well, if it's total distance, it's going to be the distance that we go in a positive direction and the distance we go in a negative direction. So you can think of total distance is equal to the positive distance plus the negative distance. So in this case, this would have been the integral of the absolute value of t. Not displacement, because remember, displacement is where you end up. So that means you have to that's positive minus or plus the negative. And that'll tell you we went 10 in the if it was just where would the bug end up? Well, he went 12 in the positive direction and 1 in the negative direction, so he ended up at 11. That's where he ended up. But what was his total distance? He went 12 that way and 1 this way, so he went a total of 13 spaces. So he traveled 13 spaces even though he ended up at 11. So there's 13. Notice that 11 is right there because that would have been your other answer. And then the other answers are all just gibberish.
So is displacement the same as the total distance?
No, those are two different ideas.
What were you saying with displacement?
Displacement is I'll do this. The positive movement minus the negative movement. So you'd find however far he went in one direction, it's basically you're going to subtract the two different measurements. This one you're going to add them together. This one you're going to subtract them together.
So for the displacement, if we were trying to take displacement, it went 3 up, and then we don't count that middle portion because it stayed constant.
His velocity stayed constant, but his velocity was 3. So the velocity, he still went a total 3, whatever it was per whatever. So he started here, he went from 0 to 3, and then after 2 seconds, or if it's in seconds, he went from 0 to 3. And then at 3 seconds, he went 3 more because his velocity was 3. So he went from 0 to 3, from 3 to 6, 6 to 9, 9 to 12, and then he went from 12 back down to 11.
But wouldn't displacement be 0? Because he didn't move at all.
He's still moving here. Velocity is constant. It's like putting your car at 55 miles an hour and putting on cruise control. Are you moving? Yeah. So what the bug did, and I might not have explained it right the first time. What the bug did is he put it on cruise control from 2 to 3, or from 2 to 4. He put it on cruise control at 3 for those 2 seconds.
But didn't he still end up at 0?
No. Because the areas under here are how he keeps on. He started here. He went 3. Then he went a total of 6. So he's at 9 now. Then he went 3 more. So he's at 12. and then he turned around and came back 1 to 11. So that's that first triangle. That's the rectangle. That's the second triangle. That's the third triangle. So, yeah, he still moved. He just ended up there. Yep. Yes. No, this is showing you how fast he's moving. And that's why we have to figure out the areas underneath the curve in order to figure out how far he's gone. Because remember, velocity is a derivative of position. So in order to figure out position, we have to integrate. And integration is finding areas under curves. So that's why we're finding areas under curves at that point.
So, how do you know that it's 3, 6, and 3? How did you find those sums?
That's 2. That's 3. The area of a triangle is 1/2 base times height, which is 1/2, in this case 2 times 3. That's a 1, so it's a 3. So that's how I figured out the area there. So I just calculated the area of that triangle. So in a graph like this, that's what you want to do, is just calculate the area of the triangle. All right, so that's 8 and 9. All right, number 3. We have f prime. Is this negative or positive? So when you're analyzing a graph like this, when f prime is 0, what do we call that point? It's a critical. That's a critical point right there, and that's a critical point right there. Now, what do critical points give you? Extrema. But you're right, it changed in direction as well. Now, in this case, the derivative is negative there, it's positive there. If I go from negative to positive, think of the roller coaster. Negative to positive. Am I going to get a minimum or a maximum? So I need a minimum at -2, and I'm going from a negative or a positive to a negative here. So what am I going to get here? A maximum, which means roller coaster means it's increasing and then it's decreasing. Now, when the slope is equal to 0, what is this point on the graph of the derivative? I'll give you a hint. Points of inflection. Because that's where the slope is equal to 0. So I need a point of inflection at 0. So if I look through these groups, the first thing I want to do is I want to find a minimum at -2 and a maximum at +2. Does this have a minimum at -2?
Yes.
Graph A?
I mean, that is the minimum. Of the graph.
No. Because if I go -2, it's here. There's still stuff there. It's not a minimum. Same thing with this. Linear equations don't have minimums and maximums. Now at -2, is that a minimum? A minimum is going to be the bottom of a valley. So that guy's out. Is this guy a minimum? No? Alright. So just by process of elimination, knowing that that's going to be a minimum and that's going to be a maximum, you can get to E from there. Because I do have a minimum there, I have a maximum there, and that's kind of right smack dab in the middle of being concave up and being concave down. So that kind of tells us that that would be our point of inflection. that's a great way to look at it too. This is a parabola. So this is x squared of some kind. So the the derivative is x squared, what's the integral? What's the original function? The original has to be x cubed. So instantly that eliminates these two. Because that would mean if you took the derivative of this, then all of a sudden, hey, then we get this. And then we have to take a look and say, all right, well, which ones are going to work? And then you can start looking at, all right, I would always look for the biggest things that you always want to look for when you're looking at the graph of a derivative. You want to look for minimum and maximums. And you want to look for points of inflection. And where f is increasing, and that's where f prime is greater than 0, or is decreasing, where f prime is less than 0. It's decreasing here until it gets to there. It's decreasing there. Then it's increasing all the way till it gets to the next point. So it's increasing all the way to there, and then it starts decreasing again. So if these are the big things that you look for, minimums, maximums, points of inflection, and if it's increasing or decreasing. If you look for those big three things, you're going to be able to pick them out of a graph, knowing that you're given f prime. Well, if this was like, that could happen. If they would have given you this, a parabola that was opened up, that would give you a positive parabola, which means when you integrate it, you'd get a positive cubic function. And then there's your positive cubic functions. So it'd be one of these two. And one of them would be right, so they'd obviously change the graph to make it right. You still, after you make that determination, and this one, I love that thinking that, all right, that's a negative quadratic, so the original has to be a negative cubic. And that makes it E, and that makes it perfect. And that's a great way to look at this. 2 seconds later, you're done. You move on to the next one. If you don't get that, you got to look for minimums, maximum, points of inflection, increasing, decreasing. We're good? We're okay with that one? I cannot stress enough. If you're looking at a graph, you want to look at the ideas of a graph. And we're going to talk, I'm going to hit that more and more and more and more and more as we go. Oh boy. All right, here's our graph. There's our graph of f, which can be the derivative of the graph. Now, when you're looking at a graph, when you're looking at f, what do you think we want to look for? Now, what characteristics of the graph do we want to look for? We want to find a max or a min on the graph itself. Now, where is that? Right around there? So we want to find a graph that has, and well, what's the tangent line? What's the slope of the tangent line? 0. So I know f prime has to be equal to 0 there. So which graphs, there's only one of them, it only has one maximum that we see. So which one only hits the x-axis in one spot? A, C, and E So B and D are gone. So now, if it's increasing here, do you agree that it's increasing? So what should the velocity, or what should the derivative be? The if f is increasing, f prime is positive. So from here to here, f prime should be greater than 0. From here to here, f prime should be less than 0. Now, here f prime is less than 0. Is that what we want? No, that guy's gone. Here, is this a constant? No, that's not a constant rate of increase. You can even get rid of that one. So we can go from there. This tells me that f is increasing. This tells me that f is decreasing. Just because? Let's try to get a better answer than just because. All right. Any questions on that one? All right, the graph of the function f is shown in the figure above. Which of the following statements is true? And we're looking at A. Okay, so we're looking at A. For the first one, the limit at A is equal to the limit at B.
No, because there's no limit at B.
Right, so that limit doesn't exist, so that guy's gone. So limit at A, is the limit at A true equal to 2? Is it both going to 2? All right, that one's true. Now I want to go through quickly, just quickly, the last couple ones here. The limit at B, we already figured out it doesn't exist. A two-way limit like this doesn't exist. So that the limit does not exist. So that one's bad there. And again, the limit does not exist. But we already figured out that the limit does exist there. No. It does exist. So B is the only one that actually makes any sense whatsoever. Yes?
So it will not exist if there are 2 points at...
Right, if there's a jump like this, because remember, for a two-way limit to work, they both from the left and from the right have to be going to the same number. And in this case, they're both going to 2, even though the function doesn't exist there.
So it doesn't matter if the circle's filled out or not?
Nope, it doesn't. Limits don't matter. It doesn't matter if the point's there or not. It just matters. Remember what limits are. Limits are looking at, you're not looking here, you're looking in your peripheral vision. You're looking what's going on this way, what's going on this way. So this guy's going to 2, this guy's going to what? To 1. They don't agree. So it's like, bam, doesn't work. We want limits to do this. Yes?
So if it was approaching B from the left, it would be 1, and if it was approaching it from the right, it would be 2.
Absolutely. We can do the one-sided from the left and from the right, but we can't do the two-sided. Because remember, a limit has to agree from the left and the right. Good? Ish? All right. Keep that with your stuff. Yeah, yes, ma'am. The free response? We're going to start looking at those right now, actually. All of these were actually from 1997 and 1998. No. Calculus has not changed since the 1700s. You're just fine. You'll be fine. Don't worry. I gotta figure out where all my extra is. All right. Now, we're not going to have a lot of time to actually go over the actual problem right now. But what I want to do